Welcome! In this session, we'll explore problem number 785, is graph bipartite? We'll dive into the concept of bipartite graphs, understand the problem requirements, and discuss efficient approaches to solve it. Let's get started. In this problem, we are tasked with determining whether a given graph is bipartite. The graph is represented as an adjacency list, where each node points to a list of other nodes it is connected to by edges. A graph is considered bipartite if we can divide its nodes into two distinct sets, such that every edge connects a node from one set to a node in the other set. If this condition is satisfied, we return true, otherwise, we return false. To better understand this, let's look at an example. Suppose the input graph is represented as 1 3, 0 2, 1 3, 0 2. In this case, the output is true, meaning the graph is indeed bipartite. Here's why the first example graph is bipartite. The nodes can be divided into two sets, 0, 2, and 1, 3. Each edge in the graph connects a node from one set to a node in the other set. For instance, the edge between nodes 0 and 1 connects node 0 from the first set to node 1 in the second set. Similarly, the edge between nodes 1 and 2 connects node 1 from the second set to node 2 in the first set, and so on. Importantly, no edge connects two nodes within the same set, which satisfies the definition of a bipartite graph. Now consider a second example where the input graph is 1 2 3, 0 2, 0 1 3, 0 2. This time, the output is false, meaning the graph is not bipartite. The reason the second example graph is not bipartite becomes clear when we try to divide the nodes into two sets. Suppose we place node 0 in the first set. Then, its neighbors, nodes 1, 2, and 3, must all go into the second set. However, node 2 is also connected to node 3, meaning these two nodes would end up in the same set, violating the bipartite condition. Therefore, it is impossible to separate this graph into two disjoint sets where all edges connect nodes from one set to the other. Let's also examine a third example, a graph represented as. Here, the output is true because the graph contains only one node and no edges. Without any edges, there are no conflicts that would violate the bipartite condition, making this graph trivially bipartite. Now, let's review some important constraints and edge cases for this problem. The graph has between 1 and 100 nodes, and each node can have up to n1 neighbors, where n is the total number of nodes. The graph is guaranteed to be undirected, meaning if node j is a neighbor of node I, then node I must also be a neighbor of node j. Additionally, the adjacency list for each node will not contain duplicate entries. As for edge cases, a completely disconnected graph, where no nodes are connected, is always bipartite. Similarly, a graph with a single node and no edges is also bipartite. However, if a graph contains an odd-length cycle, it cannot be bipartite. Finally, a graph with multiple disconnected components can still be bipartite, as long as each component satisfies the bipartite condition independently. To determine if a graph is bipartite, we aim to divide its nodes into two sets such that no two nodes within the same set are connected. This can be visualized as a two-coloring problem, where the goal is to color the graph using two colors in a way that no two adjacent nodes share the same color. First, we considered a brute force approach. The intuition here is to generate all possible ways to divide the nodes into two sets and check if every edge satisfies the condition. However, the computational cost of this method is prohibitive. With 2 to the power of n subsets to explore, its time complexity is exponential, making it impractical for larger graphs. Next, we have the BFS-based approach, which is the strategy we ultimately selected. The idea is to traverse the graph using breadth-first search while attempting to color nodes alternately. Starting from any unvisited node, we color it with one color and its neighbors with the opposite color. If any conflict arises, such as two adjacent nodes having the same color, the graph cannot be bipartite. An important observation here is that if the graph is disconnected, we need to apply this process to each connected component individually. This ensures the entire graph is covered. BFS provides a time complexity of O(V plus E), where V is the number of vertices and E is the number of edges. It's efficient and well-suited for handling large graphs, which is why it emerged as a strong candidate. In addition to BFS, we also examined the depth-first search, or DFS, approach. Like BFS, DFS attempts to color the graph while traversing it, ensuring no two adjacent nodes share the same color. The main difference here is that DFS relies on recursion, making it conceptually simpler to implement. The time complexity remains O, V plus E, which is identical to BFS. However, DFS carries the risk of stack overflow for very deep recursive calls, especially in large graphs. Another potential approach is using the union-find data structure, also known as disjoint set union. This method groups nodes into two disjoint sets and checks for violations. If two nodes in the same set are found to be connected, the graph is not bipartite. While optimized union-find operations are quite efficient, with a complexity of O, alpha, V, where alpha is the inverse Ackermann function, the method can be more complex to implement and less intuitive compared to BFS or DFS for this specific problem. Ultimately, we selected BFS for its efficiency, clarity, and ability to handle disconnected graphs without the risk of stack overflow. Its iterative nature makes it easier to debug and implement, giving it a clear edge over the other options. The key insight in solving this problem was recognizing that bipartiteness is equivalent to a two-coloring task. This realization reduced the complexity of the problem to a graph traversal exercise, where we simply need to check for consistency in node coloring. BFS proved to be particularly effective because it naturally handles disconnected graphs by iterating over all connected components. Comparing the methods, BFS stood out for its iterative design, which avoids the potential stack overflow issues of DFS. While union-find is efficient in theory, its additional complexity was unnecessary since BFS already provides a straightforward and effective solution. Brute force, on the other hand, was quickly ruled out due to its infeasibility for larger graphs. By choosing the BFS-based two-coloring approach, we achieved the best balance between efficiency, clarity, and ease of implementation. This strategy not only meets the problem's constraints but also simplifies debugging and ensures scalability, making it an ideal choice for verifying whether a graph is bipartite. To determine if a graph is bipartite, we use the two-coloring approach. This means we assign one of two possible colors to each node, ensuring that no two adjacent nodes share the same color. If we can successfully assign these colors, the graph is bipartite, otherwise, it is not. The first step in this process is representing the graph. We use an adjacency list for this purpose, as it provides an efficient way to store the graph while allowing quick access to the neighbors of any given node. For example, if the graph contains edges like 1 to 2, 2 to 3, and 3 to 4, the adjacency list representation would look like this. Node 1 connects to Node 2, Node 2 connects to Nodes 1 and 3, Node 3 connects to Nodes 2 and 4, and Node 4 connects to Node 3. With this representation, we can now proceed to initialize the necessary data structures for our algorithm. Next, we set up the data structures needed for the algorithm. First, we use a dictionary called color to keep track of the color assigned to each node. The keys in this dictionary represent the nodes, and the values are either 1 or -1, representing the two colors. Initially, all nodes are unvisited, so we set their colors to none. Additionally, we use a queue to facilitate breadth-first search, or BFS, which allows us to explore the graph level by level. Once these structures are in place, we can begin the BFS process for coloring. As we iterate over all nodes, we handle disconnected components by checking if a node is already colored. If it's uncolored, we assign it the first color, such as 1, and enqueue it to start the BFS process. During BFS, we dequeue a node and explore its neighbors. If a neighbor is uncolored, we assign it the opposite color of the current node and enqueue it. However, if a neighbor is already colored and has the same color as the current node, we know the graph is not bipartite. This process ensures that we validate the two coloring for all connected components of the graph. BFS is particularly well suited for this task because it explores all nodes at the same distance from the starting node before moving to the next level. This makes it straightforward to alternate between the two colors for adjacent nodes. The use of two colors is essential because bipartite graphs can be divided into two distinct sets where no two nodes in the same set are adjacent. For graphs with multiple disconnected components, it's important to handle each component independently, ensuring that each one is bipartite. The algorithm relies on three main data structures: the adjacency list, which efficiently stores the graph and provides quick access to neighbors, the queue, which supports BFS by processing nodes level by level, and the color dictionary, which tracks the color assigned to each node, starting with all nodes initialized to none. In terms of complexity, the algorithm is efficient. The time complexity is O, V plus E, where V is the number of vertices and E is the number of edges, as BFS visits each node and edge exactly once. The space complexity is O, V, which accounts for the storage of the color dictionary in the BFS queue. Here, we start by importing the DEEC class from the Collections module, which will help us implement a breadth-first search, or BFS. Inside the solution class, we define the isBipartite method, which takes a graph as input. The first step is to initialize a color map, where each node starts uncolored, represented by -1. This map will help us track the color assigned to each node as we traverse the graph. Next, we define a helper function called BFS that takes a starting node as its parameter. This function will perform a BFS traversal to determine if the graph is bipartite. Within the BFS function, we begin by initializing a queue with the starting node and assigning it the color 0. Then, we enter a while loop that continues as long as the queue is not empty. At each step, we dequeue a node, check its neighbors, and attempt to color them with the opposite color of the current node. If we find a neighbor already colored the same as the current node, it means the graph is not bipartite, and we return false. If no conflicts are found during this process, we return true, indicating this part of the graph is bipartite. To ensure the entire graph is bipartite, we need to handle the possibility of multiple connected components. For this, we iterate through all nodes in the graph using a for loop. If we encounter a node that hasn't been colored yet, it means we have found an unvisited component. In this case, we call the BFS function starting from that node. If the BFS function returns false for any component, it means the graph is not bipartite, so we immediately return false. However, if all components pass the bipartite check, we return true at the end, confirming that the entire graph is bipartite. This implementation ensures we comprehensively check all nodes and their relationships, even for graphs with multiple disconnected components. Here, we begin by importing the necessary libraries and defining our solution class. The key method isBipartite takes a 2D array graph as input, where each element represents the neighbors of a node in the graph. First, we determine the number of nodes, n, and create an array color to track the coloring of each node. We initialize all nodes with -1, indicating they are uncolored. Next, we loop through each node to ensure all components of the graph are checked. If a node is uncolored, we initialize a BFS process starting from that node. A queue is used to explore the graph level by level, and the starting node is assigned a color of 0. Inside the BFS loop, we dequeue a node and check all its neighbors. If a neighbor is uncolored, we assign it the opposite color and add it to the queue for further exploration. However, if a neighbor is already colored and has the same color as the current node, we immediately return false, as this violates the conditions for a bipartite graph. The BFS process continues until the queue is empty, ensuring that all connected nodes in the current component are checked. If we successfully color the entire component without conflicts, the loop moves to the next uncolored node, if any exist. Once all components of the graph have been processed, and no conflicts in coloring were found, we return true, indicating that the graph is bipartite. This implementation ensures that every connected component is validated, and the use of BFS guarantees efficient traversal while systematically checking for the bipartite property. Here, we have a simple bipartite graph represented by the adjacency list, 1302, 1302. The graph consists of 4 nodes, where node 0 connects to nodes 1 and 3, node 1 connects to nodes 0 and 2, node 2 connects to nodes 1 and 3, and node 3 connects to nodes 0 and 2. To determine if the graph is bipartite, we initialize some variables. First, n is set to 4, representing the total number of nodes. Next, we create a color array initialized to -1, -1, -1, -1, where -1 means the node is uncolored. We then begin our outer loop to check each node, starting with node 0, which is currently uncolored. This triggers a breadth-first search, or BFS, starting from node 0. In the BFS for node 0, we initialize the queue with 0, and color node 0 as 0, updating the color array to 0, -1, -1, -1. When we dequeue node 0 and visit its neighbors, nodes 1 and 3, we color them as 1, resulting in color equals 0, 1, minus 1, 1, and updating the queue to 1, 3. Next, we dequeue node 1 and visit its neighbors, nodes 0 and 2. Since node 0 is already colored differently, there's no issue. We then color node 2 as 0, updating the color array to 0, 1, 0, 1, and adding node 2 to the queue, which now becomes 3, 2. When we dequeue node 3 and check its neighbors, nodes 0 and 2, we find that both are already colored differently, so no conflicts occur. Finally, we dequeue node 2 and confirm that its neighbors, nodes 1 and 3, are also colored differently. At this point, the BFS for node 0 is complete, and all nodes are processed. For the remaining nodes, nodes 1, 2, and 3 are already colored, so we skip them. Since no conflicts were detected, we conclude that the graph is bipartite and return true. Now, let's analyze a non-bipartite graph represented by the adjacency list 1, 2, 3, 0, 2, 0, 1, 3, 0, 2. This graph has 4 nodes. Node 0 connects to nodes 1, 2, and 3, node 1 connects to nodes 0 and 2, node 2 connects to nodes 0, 1, and 3, and node 3 connects to nodes 0 and 2. As before, we initialize n to 4 and the color array to -1, -1, -1, -1. Starting with node 0, which is uncolored, we begin our BFS with start equals 0. In the BFS for node 0, we initialize the queue with 0, and color node 0 as 0, updating the color array to 0, -1, -1, -1. When we dequeue node 0, we visit its neighbors, nodes 1, 2, and 3, and color each of them as 1. This updates the color array to 0, 1, 1, 1, and the queue to 1, 2, 3. Next, we dequeue node 1 and check its neighbors, nodes 0 and 2. Node 0 is already colored differently, so there's no issue. However, node 2 is already colored the same as node 1, which creates a conflict. This indicates that the graph is not bipartite. As a result, we immediately return false. Here, we examine a disconnected graph represented by the adjacency list 1, 0, 3, 2. This graph has 2 disconnected components. In component 1, node 0 connects to node 1, and node 1 connects back to node 0. In component 2, node 2 connects to node 3, and node 3 connects back to node 2. We initialize n to 4 and the color array to -1, -1, -1, -1. Starting with node 0, which is uncolored, we initiate a BFS for component 1. For component 1, we initialize the queue with 0, and color node 0 as 0, updating the color array to 0, -1, -1, -1. We dequeue node 0 and visit its neighbor, node 1, coloring it as 1. This updates the color array to 0, 1, -1, -1, and the queue to 1. Next, we dequeue node 1 and check its neighbor, node 0, which is already colored differently. This completes the BFS for component 1. Now, we move to node 2, which is uncolored, and start a BFS for component 2. We initialize the queue with 2, and color node 2 as 0, updating the color array to 0, 1, 0, -1. We dequeue node 2 and visit its neighbor, node 3, coloring it as 1. This updates the color array to 0, 1, 0, 1, and the queue to 3. Finally, we dequeue node 3 and check its neighbor, node 2, which is already colored differently. With all components processed and no conflicts detected, we conclude that the graph is bipartite and return true. To analyze the time complexity of the algorithm for determining if a graph is bipartite, let's break it down step by step. First, we have the outer loop, which iterates over all the nodes in the graph. If there are n nodes in the graph, then this loop ensures that every single node is considered. In the worst-case scenario, if the graph is disconnected, the loop ensures that all connected components are accounted for. Now, within this loop, a breadth-first search, or BFS, is performed for each unvisited node. BFS processes every node and its neighbors exactly once. This means that, across all BFS calls, the time taken to process nodes is proportional to n, and the time taken to traverse edges is proportional to m, where m represents the number of edges. Combining these, the overall time complexity of the algorithm becomes O, n plus m, as each node and edge is visited at most once during the BFS traversal. Now, let's shift our focus to the space complexity of the algorithm. The first component contributing to space usage is the color array, which is used to store the color or state of each node. Since the graph has n nodes, this adds a space requirement of O(n). Next, the BFS queue, which temporarily holds nodes to process, can grow up to the size of the largest connected component in the graph. In the worst case, this queue could hold all n nodes, contributing another O(n) to the space complexity. Additionally, the graph itself is represented as an adjacency list, which requires memory proportional to the number of nodes and edges. This adds O(n plus m) to the total space usage. Therefore, when we add these contributions together, the overall space complexity of the algorithm is O(n plus m), accounting for the color array, the BFS queue, and the adjacency list representation of the graph. It's helpful to compare this efficient BFS-based solution with a potential brute force approach. A naive solution would involve trying to partition the graph into two sets by generating all possible subsets and verifying whether the conditions for bipartiteness are satisfied. This brute force method would require exponential time, specifically O(2 to the power of n), as it explores all combinations of node partitions. In contrast, the BFS-based approach is significantly more efficient, with a time complexity of just O(n plus m). This is because it processes each node and edge exactly once. While depth-first search, or DFS, could also be used to solve this problem with a similar time complexity, BFS is often preferred for its iterative nature and its ability to handle graph traversal in a more structured and predictable way. To further understand the algorithm's performance, let's look at the best, average, and worst-case scenarios. In the best case, the graph is already bipartite, and a single BFS traversal efficiently processes all nodes and edges. Even in this scenario, the time complexity remains O(n plus m), since every node and edge needs to be visited. In the average case, regardless of whether the graph is bipartite or not, the algorithm still processes all nodes and edges to determine the graph structure, resulting in the same time complexity of O(n plus m). Finally, in the worst case, the graph is disconnected and consists of multiple connected components. Here, BFS is performed for each component. However, even in this scenario, every node and edge is still processed exactly once, so the time complexity remains consistent at O(n plus m). To solidify the analysis, let's look at the mathematical reasoning behind the big O complexity of the BFS-based solution. Each node in the graph is visited exactly once during BFS, contributing a time complexity of O(n). Each edge is traversed twice, once for each endpoint, leading to a time complexity of O(m) for edge traversal. Combining these, the total time complexity becomes O(n plus m). On the space complexity side, the adjacency list representation of the graph, the color array, and the BFS queue together dominate the memory usage, resulting in a total space complexity of O(n plus m). This linear relationship with the number of nodes and edges makes the algorithm highly efficient for both sparse and dense graphs, providing an optimal solution to the bipartite graph problem. When working on bipartite graph problems, there are some common pitfalls to avoid. First, it's crucial not to assume that the graph is connected. A graph can consist of multiple disconnected components, and each of these components needs to be checked individually to confirm two-colorability. Another mistake is overlooking odd-length cycles. Remember, a graph is not bipartite if there's an odd-length cycle, so your BFS or DFS implementation must explicitly account for this. Incorrect color assignment is another frequent issue. This happens when logical errors in your traversal lead to improper alternation of colors, which can skew your results. Additionally, don't ignore self-loops. A self-loop, where a node has an edge pointing back to itself, automatically makes the graph non-bipartite, and skipping this edge case can lead to flawed conclusions. Lastly, be mindful of your implementation's efficiency. For large sparse graphs, using an adjacency list is far superior to an adjacency matrix in terms of both memory usage and traversal speed. To excel in interviews, it's important to fully understand and articulate the concept of a bipartite graph. You should explain that it involves dividing nodes into two sets where no edges exist within the same set, and you should be ready to clarify why odd-length cycles prevent bipartiteness. When choosing an algorithm, while both BFS and DFS are valid, BFS is often preferred in interviews because its level-based traversal makes color assignments more intuitive. You should also be prepared to discuss edge cases, such as disconnected graphs, self-loops, or even graphs with no edges. Addressing these thoroughly shows strong analytical skills. Finally, don't forget complexity analysis. If you're using adjacency lists, the time complexity is O, V plus E, where V is the number of vertices and E is the number of edges. Mentioning this demonstrates a solid grasp of the algorithm's efficiency. Bipartite graph problems are part of a broader family of graph-related challenges. For instance, LeetCode 785, is graph bipartite, is the foundational problem. LeetCode 886, possible bipartition, builds on this concept, while LeetCode 261, graph valid tree, explores connected components, and LeetCode 207, course schedule, focuses on cycle detection in directed graphs. Beyond this, it's useful to understand the trade-offs in algorithm selection. The BFS approach is highly visual and straightforward, processing nodes level by level, which makes it easier to debug and ideal for interviews. However, it requires additional space for the queue. On the other hand, the DFS approach can be more memory efficient for large but shallow graphs, but it introduces challenges like handling recursion depth carefully. Choosing the right approach depends on the problem's context and constraints. Finally, there's the union find approach, also known as the disjoint set union method. This is an alternative way to check if a graph is bipartite, though it's less intuitive than BFS or DFS. It involves maintaining and updating the union find structure, which can be more complex to implement and explain. While it's not commonly asked in interviews, it's a powerful tool for competitive programming due to its efficiency in managing connected components. Understanding this method adds depth to your problem-solving toolkit, especially for scenarios where traditional graph traversal methods might not be as straightforward to apply. Great job! Today, we learned about bipartite graphs and how to determine if a graph meets the criteria. This concept is critical in graph theory and can help you solve many related problems. Thanks for joining, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!